on the last session. The first presentation is from Jasper Schurman, University of Amsterdam. He will talk about the light-assisted CO2 reduction in an automated photoreactor system coupled to carbocation chemistry. The project is, this presentation is related to Project Qatar. Just to...
Any questions? Thanks. Yeah, thanks for that nice introduction. I'm not really used to talking with a microphone, which says a lot about my singing ability, so I'll keep it with presenting, I think. So I'm Jasper. I'm a PhD student in the Qatar project that Igor told you about this morning. We're trying to make this automated system where we want to continuously convert CO2 and couple it with AI. I've been mostly involved in the reactor design, and basically working on the reactor design, we came up with a project that we published, which has a lot of different aspects that are all in the title. And I will go over them one by one, and hopefully in the end it all comes nicely together. I can change the slides. What? One second. Yeah, I think we saw enough carbon dioxide today, and it's already stopping. It's working.
No, it's okay. It's okay.
It's working. Cool. So we saw a lot of large-scale applications, I think. We're talking about tons, liters, but in Amsterdam, we work mostly on synthetic methodology, so trying to make new functional groups in materials or in molecules. And we typically talk about smaller scales like millimoles, milligrams, and if we're lucky, maybe a few kilograms. So that's also for this project where we focused application on not the fuels through Fischer-Tropsch, for example, but more on the higher value-added compounds like agrochemicals and pharmaceuticals. So there are several ways to convert the carbon dioxide. We saw already electrochemical, photochemical, and thermal energy. And for this project, we tried to then use both the thermal energy and the photochemical energy. I know there is this term photothermal, which has a lot of definitions in literature, and a lot of people contradict each other, so I will not go in that area. But sometimes you need like an initial thermal boost to actually see an effect of the light. Sometimes the light can actually heat up your catalyst bed locally. So it's really the interplay between the two effects that we try to combine. And so one way to actually screen new photocatalysts is by using a batch reactor. So in that case, you load your solid catalyst in the reactor, you put your CO2, your reductant, which can be water, can be hydrogen, you let it go to reaction conditions, so temperature and light, and then you wait a certain amount of time, and then after that you collect your products and you analyze how well your catalyst did. There are a few disadvantages of this, and I think the most important one is that as soon as you start the reaction, you have to wait until it's over, and you cannot use your system in the meantime. But luckily, I saw a lot of presentations already have continuous flow. So our group also works a lot with continuous flow. It has a lot of benefits in that sense. You can change the reaction conditions. So for example, if you want to use solar light, which is the idea with this project, if a cloud passes by, you can actually, for example, change the flow rate, so you can increase the residence time, so you can keep constant conversion within your reactor. You also have like narrow channels, so higher surface to volume ratio, so you can heat up your reactant stream very fast and also cool it down if you want that. And then since we're working with light, narrow channels also provide better light radiation off your channel rather than if you have a very big local patch. When I looked into literature on systems to basically screen different types of catalysts, I encountered this a lot. So you basically take your solid catalyst, you disperse it in a liquid, and then you bubble gas through it. which is actually very convenient because you can control the mixing of the liquid. You can make sure the gas contacts well with the catalyst. You get these nice bubbles, so you have a lot of interfacial area, and the gases go out and you can analyze it. But it also has some downsides. For example, products can accumulate within the liquid, and the liquid can, of course, affect the properties of the catalyst itself and then affect the performance. And by changing the liquid just with a solid catalyst powder also brings some challenges. If you just put powder, the gas will not want to interact with the powder. It will want to find a way of least resistance and basically go straight out to the outlet without interacting with the catalyst. You can try to force it basically through the powder, but if you have a very fine powder, you get a very high pressure drop. And in that sense, it's not the easiest system to work with. And since we're working with photothermal, we want to heat it up and irradiate at the same time. So what's typically been done is you heat it from one side and then the other side is transparent and you put your light there. But then you can get the temperature gradient within your catalyst bed, which also has actually been proven to affect the performance of the catalyst. No? Okay. It's okay like this. So one of the ideas within the project was to develop then a reactor where we can screen this catalyst. And to tackle this inhomogeneous heating, we came up with this relatively simple idea, I would say. We made an oil tank with a quartz window, so we can irradiate inside the oil tank, and the oil that we use is also transparent, at least for the wavelengths that we're interested in. And then inside this oil tank, we can insert these glass reactors. So we buy them from a company called Little Things Factory. It's just a glass reactor with a channel carved in there. And you can basically insert it in the oil. In that case, you get heating from multiple sides. So at least you minimize the temperature gradients within the reactor. It also gives rise to a modular system. You can imagine like any reactor that fits in the oil tank, you can fit in if you want to use a tube or anything else. You just insert it in the reactor and you can start screening. Then to tackle the high pressure drop and the short circuiting, we actually took inspiration from cam beads. I don't know if anyone is familiar with it, but it's basically AbbVie developed these cam beads to weigh off very small quantities in high throughput experimentation. So what they do is they take regular glass beads, they take catalyst powder, they put them together and they mix. And after mixing them, you get a nice even layer of catalyst on your glass bead. And we thought we could use this to basically artificially increase the size of our particles without having to use a lot of catalyst. And by doing this, we can force the gas to run over the catalyst and minimize the pressure drop. And on the pictures, like on the left, you can see the normal glass bead. There's still some glue residue on there. And then on the right, you can see it after doing this coating procedure. So you can see a very nice uniform layer on the bead. And it also allows for very reproducible loading and low amounts of catalyst to go actually in the reactor. And another thing we wanted to make sure of is that we always work under the same conditions. And with like upcoming self-driving labs and our lab also working a lot on this, we wanted to implement automation. So we took control over the flow rates, the light intensity, the pressure, and also the temperature. And where we could, we actually developed the materials in-house. So for example, for the pressure, we made this back pressure regulator that we could control with 3D printing and Arduino. So it's cheap, and also the publication provides all the details on how to make it, so any lab who wants to can do it. We also have a graphical user interface. So if you want to run an experiment, it's really, you have to turn everything on and go to the computer, set the parameters, and the system automatically goes to the conditions, and then you can start analyzing the results. So far on actually the development of the reactor, and then we started screening different catalysts. We find it very easy because we could just take the glass reactors, load them with catalyst, and then swap them in and out, and then start running different conditions. I want to highlight one of the catalysts, which are gold nanoparticles on titanium dioxide. So this catalyst makes carbon monoxide. And you can see in the graph that shows the productivity against the conversion that it needs more or less 160 degrees to actually start producing something. So you really need this initial kick of thermal energy to also see an effect of the light. And that's also, of course, due to the light source that we use. It's like white LEDs, more or less intensity of 2 suns. If you go to higher intensities, of course, you need lower temperature. But you can see that the higher you go in temperature, the more CO you produce. And if you turn the light on, you actually get this initial conversion of CO2, which is not just from heating up the oil. We check the temperature of the oil. It's really local effects in the catalyst bed that the heat or that the light induces, and that boosts the conversion. So we could basically map out how much CO we make with this catalyst, and then this got us thinking like, okay, we have the CO in relatively low quantities. What can we do with it now? And we really were targeting the value-added compounds. And that's how we came up with this fed batch reactor where we want to perform combinative cross-coupling reactions. So basically what we do is we bubble gas that's coming from the photoreactor to a reaction mixture, and then it has an outlet, of course, and then through a syringe pump we feed in one of the reactants, because it's a cross-coupling where we want to like insert the carbon monoxide. So you have compound A, compound B, and if you add them both together at the same time, they all want to react with each other. So now we have compound A in there already. We bubble the CO in, it couples with the CO, and then we add B, so you can make the product like that. And we did this for 3 different types of cross-coupling reactions, shown on the slide with different functional groups in the end. And we actually managed to get quite decent yields, I would say, out of it, proving that we can also use like a relatively low source of carbon dioxide to convert it to actually the amount of CO that we need. So we don't need to store CO also. That's also a benefit. Of course, you still need hydrogen in this case, but ideally from water and CO2, you can produce CO on demand, and then after that, you just have the CO2 and water stored. So for the Qatar project, we actually developed this modular system to test different catalysts for carbon dioxide production, but we wanted to take it one step further to see if we can actually also concentrate the light on the catalyst channel itself. So since we have this oil tank and previous work on luminescent solar concentrator reactors, we try to combine the two. So luminescent solar concentrator is basically a matrix in which a dye is embedded. You shine light on the matrix, the dye absorbs the light and then re-emits the light again. And it's get emitted in all directions. And since there is a difference in a refractive index between the matrix and the surrounding air, you can get total internal reflection. So you're basically making use of a waveguide that guides the photons to the sites where you can put your reaction channel. And in that case, you can concentrate the light and at the same time also down convert the wavelength of the light. So you're changing the energy of the light, and ideally you can match it then with the absorption wavelength of the catalyst. So you can boost production in 2 ways. One is the light concentration, and the other one is the down conversion of photons to match it with the catalyst. So that's ongoing. It depends a bit on if we can find a good catalyst that matches well with the dye. But we noticed if we put dye in the oil that we use to heat up the reactor, it's stable. It seems to be shining very red and bright, and some control experiments confirmed that we can concentrate the photons like that. And with that, I would like to thank a very big group and also, of course, the people in the Qatar project. And if you're interested in the project, the QR code should lead supposedly to the website. And if there are any questions, I'm happy to answer them.
Thank you. There are questions, comments? What do you think? This kind of photoreactor could be very easily commercialized?
So like the glass reactors we put in are already commercially available. It's really about getting an oil tank, and if you want temperature control out of it, you can also use like a heating plate with the oil well. We did the same kind of test. It's a bit more difficult to control with the thermal inertia, but I think it should be very cheap available. Yes.
Thank you very much. Other questions? No? If not, thank you very much again. Now, Victoria Aluvanova from the Institute of Photonic Sciences. The talk is about advancing urea quantification at the trace level within the project ICONIC.
I was working again. Sorry, Jasper.
Okay, hi. Thank you so much for the introduction. And well, the disadvantage of speaking in the end of the workshop is that a lot of people have gone through the introduction many times, and I couldn't remove most of my introduction slides, so please bear with me a little bit more on the topic of urea and the project itself. It was already presented by Ruud a little bit earlier. So please. Never mind. I will just stand here. So when we talked a little bit about a lot about the sustainability these days and so on, and many times we think about, there's a lot of things to take into account. We're talking about sustainability, but then many times we think about the carbon cycle only and all the products that are associated with the synthesis within the carbon utilization. Then there's another very important cycle, which is a nitrogen cycle and the products related to it. So what if we polarize these two and get very important CN products, and one of them is the urea, the key fertilizer in our process. And of course, we talked a lot about the Haber-Bosch and amazing reaction that was invented more than 100 years ago, revolutionized the world and solved the food crisis. And the Bochmeister, which converts half of all of the ammonia produced by this project to the urea. Both of these processes require high temperatures and high pressures. They account for lots of emissions. They account for more than 2% of energy produced globally. So we have touched on that already, and it's natural that we would like to electrify this process and create an alternative and decentralize it, as was mentioned already before. So the levels of nitrates in the groundwaters that are finally flushed into the seawater are alarmingly increasing. This causes eutrophication, health risks. This causes a lot of extra energy that is needed to purify the water to make it drinkable, and so on and so on. But then another point is that when we're talking about the carbon source, we usually think about the CO2 that is being accumulated in the atmosphere, right? Global warming and so on. But we sometimes forget that a huge part of the CO2 is being absorbed by the ocean. And so it's kind of buffering the CO2 levels in the atmosphere, which causes another very important problem, the acidification of the ocean. So the pH is changing because the CO2 is being converted to bicarbonates. And most of the biological systems, they usually prefer alkaline environment for surviving, and that causes huge threats to the whole marine ecosystems in general. And it's something that we have to keep in mind, but we also see it as an opportunity and as a source of the carbon that we can use and we can convert into the products of interest. So this is the idea that lies behind the ICONIC that was already presented before. This is the vision that we have, that we take the wastewater and we also take the bicarbonates that are dissolved in the seawater to produce urea, and at the same time remediate the environment and deacidify and purify the seawater, the wastewater at the same time. And we're lucky to have a very nice consortium that was already presented by Ruud as well. Many countries working together, many researchers working on the development of the catalysts, the characterization, testing the devices, and also the life cycle assessment of the whole process. So the bicarbonate itself is not very easy to reduce, thermodynamically speaking. So we would need to divide our reaction into two steps. Something very typical for bicarbonate reduction itself, apart from this process, which is usually it happens with the use of a bipolar membrane or any other proton source that you might want to use to recover the CO2 in situ inside of the cell from the carbonates into the form of the CO2 into the gas. That is later reacted with the nitrates to, in this case, to be co-reduced to the urea. So this is the division of the steps in the project that we're going for. So, okay, coming back to the urea, this is something for myself to remind what is urea as I'm not a chemist, something that I need to remember. The reduction of CO2 and nitrates to urea is a very complex reaction. It requires 16 electrons, so it's pretty complex. And on the way, you have all the possible byproducts that you might think you have. So you have nitrate reduction byproducts, nitrites, ammonium, and so on, hydroxylamine. You have all the possible carbon CO2 reduction byproducts. You have hydrogen, of course, always. So you end up with this soup of liquid and gaseous products altogether, within which you have to identify, detect, and quantify your main product of interest, which is urea. And here I just put together some of the papers. They're not maybe, well, this is kind of a state of the art on only some of them. But first of all, I wanted to mention that this is an evolving field so far, and we do face a problem of reproducing the papers. This is normal for an evolving field, but this is something that we have to keep in mind always. Another point that I wanted to make here is that while most of the papers are focusing on high selectivity to urea, so high cardiac efficiency, they're still working at very, very low current densities. So within from 1 to 10 milliamps per square centimeter. This is very typical current densities now for this field, with a couple of exceptions, but this is very typical. What does that mean? So that basically means low current densities, means low yields, means very low concentrations. And this is something that we're dealing right now in this field, to be able to detect urea at very low concentrations, which is sub-micromolar in some cases. So we're in a desperate need of a very robust, very reproducible method that could quantify the urea at these concentrations that could not be affected by any interferences, which I will talk about. And last but not least is also very timely, because the urea stability in the electrolyte is not ideal. It could survive within some hours, but especially in the electrolytes, when it's not just pure water, the urea stability is not very high. So we cannot afford ourselves to send a sample somewhere and wait for a result and have the result back in a couple of days. We will not have proper result. So I will just quickly go through some of the methods that are suggested in general in the community. One of them is NMR, 1H NMR, 13C NMR. They're considered to be very solid, but to detect any urea at all in 1H NMR needs frequency is more than 700 megahertz, and this is a facility that not a lot of people can afford. 13C NMR was discussed in the literature with misconceptions and interferences as well, and generally the limit of detection is not very low. Then there are colorimetric methods. I will stop upon the Rees method, which is the reaction of urea with an enzyme, the Rees, that decomposes it to ammonia and CO2. And the resulting ammonia can be detected by the UVs or by the ion chromatography. I will also stop on that a little bit later. And another very common colorimetric method is the DMLTSC. It's something that is used by many research groups, and I will explain a little bit now what is happening here. So basically within this method, we have the urea that reacts with the diacetylmonoxide molecule. And this complex is then enhanced by thiazide carbazide to form a chromophore that absorbs to around 525 nanometers. And that is then detected by the UV spectrometry. And this works very well when you have pure water. As soon as you start having different byproducts, that becomes a problem. And the main one is the nitrites. It has been already discussed in the literature a lot, that the presence of the nitrites in the electrolyte leads to fading of the peak, of the color as well, and the suppression of the absorption peak, which happens because of the oxidation of the nitrate species, most probably. And we decided to reproduce that. So we checked what happens with different urea concentrations and different nitrite concentrations in a certain media, which is, let's say, 0.1 molar bicarbonate. And you see that the more urea you have, the more nitrite you have, the more suppression you have in the absorption. But then your electrolyte is usually not just bicarbonate. You have nitrates in the beginning. You have to start from something. As soon as you add the nitrates, you not only have the suppression of the peaks, but sometimes you also have the overexpression of the peaks. And this is something that happens at low nitrate concentration. When you increase it, the distribution of the error changes again. And we estimated very roughly how to translate the change in absorption to the FEs. And if you take a typical current density and you translate it in the error in the Bragg efficiency, it could lead in the error up to 30%. So this is the huge error that comes in the DMO with the nitrate interferences. So how can we deal with that? There was a method already reported that we optimized also, used and optimized, which is basically removing the nitrites with sulfamic acid. And then the sulfamic acid reacts with the nitrites and removes it in form of nitrogen gas. And indeed, in a model electrolyte, this might work. We can reduce the error quite significantly. But it only happens when you have your model electrolyte and you have all the other interferences that you might possibly have during the reaction. It's very difficult to test across all of the possible interferences. We tried, of course, the nitrites are there. We did experience some interferences with ammonia, which is another very common byproduct during the urea electrolysis. So in this way or another, the detection limit of this method is very high still. It's not very high, but it's around 3 micromolar, and sometimes we need to work with concentrations of urea that are much lower than that. I will quickly touch upon another method mostly used by our partners in TU Delft, and this work that I will show in the next couple of slides was fully made by postdoc in the group, Shilangfu. And as mentioned here, in the ideal case, when you use the ureas and you have nothing else, so you had only urea before, it's not a big deal to detect the ammonia because you had no ammonia and then you start detecting some, so you can detect it by both methods. But when you already have some ammonia in the electrolyte because the product that you just generate, then you end up detecting a very small difference, right, between the ammonia that you had before and the ammonia that you generated during the urease process. So it was checked by him in the ionic chromatography how what happens when there is no ammonia and there is ammonia present. And even though he managed to detect a small increase in the ammonia peak, still this parameter, that is basically the proportion of the ammonia that is synthesized to the urea, which is supposed to be 2 because you get 2 ammonias per 1 unit, was always more or less 2. And he was getting more or less nice results when it was injected in the ionic chromatography. With the UVVs, when there was no ammonia present initially in the electrolyte, the results were still okay, but when the ammonia was already present in the electrolyte, the deviation was much higher. So in his case, it was working quite fine with the combination of the urease and IC detection, but still the limit of detection was no less than more or less 3 micromolar, and we were dealing with something much lower than that. So for that, we built an ionic chromatography system that was built to the mass spectrography, and we optimized the system for quite a long time, and we managed to detect the urea at the concentrations down to 2 ppbs, which was something that we were very happy about. Another point is that I mentioned that the detection should be timely, and we can get most of our liquid products and byproducts and urea doing the same run, detecting ammonia, nitrites, nitrates, formic acid, formic acetates, and so on in the ionic chromatography during the same run. So this is something that we're quite happy about. We detected in the single line mode and in the scan mode. So we are monitoring the urea mass to charge ratio of 6:1 because it happens in the protonation mode. And we can detect the urea and its dimer, which is at 121 as well. So we checked this method. In this case, this is a similar matrix, but instead we fixed the urea concentration and we varied the nitrites and the nitrates now in the electrolytes. And we've seen again the distribution of different suppression and overexpression of the peaks and the DMO-TSC method. And then we injected exactly the same prepared electrolytes into the ICMS, where we had almost no error within the error bar that we have. So we were quite happy with the method. We can detect urea concentrations much lower than this, but we chose this in order to compare between the two methods. Here I just wanted to put a couple of papers from the table that I showed in the beginning. This is where they are located in the field, in the plane of the urea concentration. They're all around on the limits on some of the methods that they themselves use to quantify. Even if they're higher than that, these are usually the best results that you can get, right? Because they're published and so on. But when you're trying to develop a catalyst, when you're going from zero, you need to optimize the catalyst, the reactor, the reaction conditions, the gradient stack, and so on. Usually you have to see the trends and the concentrations that are much lower than what has been published in the state of the art so far. So this is where the proper, sensitive and timely and interference independent method is very handy. So with this, I just wanted to conclude that we do need a very reliable and sensitive method for the detection of urea, that the DMO-TSC is subject to nitrate interference at least, also to ammonia interference, and the results are variable even with treatment that we subjected our samples to. We got some pretty reliable results with the urease IC method, but the limits of detection was still pretty high. But with the ICMS, we could detect the urea down to ppb level. There are a couple of open questions that I can still discuss with whoever is interested, which is basically how the matrix, how the electrolyte is affecting the urea detection and quantification, because we managed to see that with the different concentration of the electrolyte of the ions in the electrolyte itself, we have different amount of urea that is sort of exposed, that is detectable. So that is a fundamental question that is related with also the dilution of the electrolyte that we still want to understand and discover, and I can discuss this with you whenever you want. And with that, I would like to acknowledge the iconic group, our consortium, my group, and these 9 people that were working very hard in this optimization of the methods, and you for your attention. Thank you very much.
Thank you, Victoria. Questions? Comments?
It's too late.
Maybe we have late. Okay, yes, please.
For the presentation, just about some questions about we use the decibel monoxide method. When you construct a calibration curve, do you also you make a standard calibration curve, or you take into account the presence of interference by doing standard addition, because that's what we actually trying to do in order to
Right.
suppress the effect.
Yes, but how do you know how much you have of the byproduct? So we can do that, right? We can insert initially the not only, so of course we do the calibration curve not in water, but in the, then you can also add the possible interferences, but the concentration of that interferences will affect your result as well. So as you don't know from the beginning, because we make an experiment, how much you will have, it's very difficult to predict how much you put in the beginning for the standard sample. That's my take on this, but we can do that.
Standard at our sample, so it's like we are subtracting all the interference. It's a it's a way to get rid of the interferences.
Okay, we can do that
Maybe
later,
we
but
can discuss.
it depends on what is your standard. But yeah, let's do that.
Interesting. Would like to ask if this chromatography, this ionic chromatography, you say, is it possible to use isotopes?
Yes. Yes.
You can distinguish.
Yes.
Okay.
I mean, because we have the MS. So we have the mass spectrography in the end. So we will have a different mass to charge ratio and we will be able to distinguish. We will do that for sure. Like we're not optimizing.
Oh, it's not still my idea.
Sorry.
No, because in catalysis it's very common to use isotopes to see the mechanism.
Thank you.
Questions? If not, thank you very much. Now, Vasilis Kyriakou, University of Groningen. Efficient steam electrolysis electrodes for proton-conducting ceramic electrochemical reactors. The project related to this talk is eco-olefins.
Pointer works. Let's see. Yeah. You didn't lie. It did, yeah. Can I try again? Oh, yes, there. Oh, did you see it? Got an additional picture. Maybe it works every time. Start very well. No, it's because of the arrow. Yeah. Yeah, sometimes works, sometimes don't. So I will. So hello everyone. I will dive a little bit into materials. So sorry in advance. So I will discuss, if the slides allow me. Yeah, I will discuss about steam electrodes and their importance. First of all, for our project ecologies, but in general for electrification with ceramic reactors. First, a small introduction. So I'm coming from Groningen, not originally, as you understand from my accent, I suppose. But the University of Groningen is located at the top of the Netherlands in the north. You cannot go northern than that. And this is our home. This is the Faculty of Science and Engineering, the Feriha building that is quite new, with all the problems that they are coming with the building. However, we managed to do some nice research there, and this is what I'm going to present. That's true. I will do that. Yeah, so I took this map from Electrochemical Conversion Materials Society from the platform that was coming from NVO. It's a very nice cartoon map of what we want to do in the Netherlands with the energy transition. So as you can see, we have mostly, let's see the laser works. It works, but it's very slow. Okay, but as you can see in the slide, we have, let's say, a lot of renewable electricity, which at the end we will need to find solutions about storage and transport. So in this direction, I think I will come here and push every time. So to this direction, we consider that these electrochemical membrane reactors based on ceramics can be quite useful, or at least can be part of the solution. These type of reactors, they are fueled by renewable electricity, and you can convert abundant sources like CO2, steam, and nitrogen into something useful, like chemical fuels, like syngas, ethylene, like what we do in ecolysis, but also ammonia. How can you use them? I suppose you can either use them directly in chemical industry or in the solution that you are looking for, or you can store them and utilize them later. And this is what we call seasonal storage with the form of chemicals. One type of reactors that we use, that they are practically sister technology of solid oxides. The more popular solid oxides, the protonic ceramic cells, and the so-called protonic ceramic membrane reactors. They can have several applications. I think the key advantage that they have is that they can unlock this very intriguing temperature range between 300 and 500 degrees to couple it with industrial processes. But this, of course, comes with the challenges, and one of them I'm going to discuss today. As you can see, the first schematic in A, this is something very close to what George Marnellos presented before for the coalescence concept, where you co-electrolyze CO2 and steam on different chambers in order to convert them to something like methane or other hydrocarbons. However, to do that, in such a concept, you will have to have one challenge. One of the challenges is what you see here on the top. So when you are converting CO2 with protons to some hydrocarbons, you are always producing some steam, which limits thermodynamics and kinetics about the conversion that you can have to these hydrocarbons. So the idea and the core innovation of the coalescence is that we are using a co-ionic system, a co-ionic cell. So practically part of this steam that will be produced would be again electrolyzed and produce some hydrogen. This type of concept is, I would say, a hybrid solid oxide and protonic ceramic technology. What is important, except of the CO2 side, and this is what University of Groningen and University of St. Andrews are focusing, is what is happening on the second side, where we have the steam. Someone should supply the hydrogen, the protons in this case, for the electrolysis. And these materials are very important, and they are not, let's say, at the level that we want for commercialization at this point, because we want to electrolyze steam under oxidizing environments at intermediate temperatures. So it's quite an unexplored territory. So what we want for our material is practically some properties that we call triple ionic electronic conductor. Why we want that? If we see the mechanism, I will not go in detail in the mechanism because they're still under debate about what it can do, but the major steps involve water uptake, oxygen vacancy formation, and therefore all these type of properties, if our material has them, then it is can be quite efficient. So as you see here in the first schematic, if the laser pointer can show on the top, you see that in order to split water, you need the vacancy in order to form the protons that they are going to hop through the electrolyte towards the second side. Except of that, the oxygen vacancies are very important because they're participating in the reaction and, of course, want to do water splitting. So the water uptake of the material is also quite important. So we have materials which are practically oxides, conductive oxides based on ceramics, mostly perovskites, that they can have all these properties. I was clicking for so much time that no, they are here. That they can have all these properties that we want, and at the same time, they are not containing any kind of noble metals. So if you do a literature review on what materials are existing out there for that they possess and exhibit these properties, are mostly perovskites, double perovskites, and some cases of misfit layered oxides, as they call it. So they are some kind of layered oxide materials. We are particularly interested in perovskites, particularly the one with praseodymium, nickel, and cobalt, the PNC, because it has a relatively simple structure and it has very high performance. And at the same time, we see a lot of room for improvement. So Nanon is a PhD student working in ecologies on the steam electrode. In that case, he has made huge progress on that. She started with the materials, could replicate the performance and the purity of this material, of this praseodymium nickel cobalt perovskite. I will call it PNC. But we thought that there is room of improvement, as I said. And in our case, we did something quite simple. Initially, we doped some calcium. Praseodymium is a 3+ oxide mainly. We dope with calcium 2+, and we create more vacancies. That was our initial target. You see with the XRD, after the synthesis with wet methods, that the material is quite pure phase, the regular PNC. And as we increase the temperature under wet air, we have good purity, we sustain a good purity without any signs of degradation. The calcium doped sample, however, was pure phase, but there are some very, very tiny amounts of calcium oxide. So even with a small doping of calcium oxide, we observe some secondary phases. These tend to segregate, in our case, on the surface. These are ACM images. And what Nanon did was we took the materials and we exposed them to acid, to a light acid, in order to remove selectively the calcium oxide from the surface. With gray, you see with dark gray the basic material, and with light colors, it's the ones that were treated with acid. So we have the PNC, the calcium PNC, and the light colors are representing the ones that were treated with acid. So as you see on the surface, after acid treatment, we don't have any kind of secondary phase that we're observing in the calcium sample initially. Except of cleaning the surface, this also resulted in functionalization. So the first analysis that we wanted to do was electron paramagnetic resonance to measure the concentration of oxygen vacancies. As you can see, the doped sample with calcium, as expected, had higher number of vacancies, but compared to the bare material, the bare PNC, also the acid treatment had an effect in the number of oxygen vacancies that we observed. In terms of oxygen exchange, you see from the TGA that also the oxygen exchange is more important in the doped and acid sample. And the interesting stuff came, let's say, from nowhere initially, because we couldn't expect that. So we took our materials that, as you saw in the NCM, there was nothing on top. We prepared the electrodes, and after just sintering the electrode, we observed that our surface was full of nanoparticles. First of all, we had to understand what type of nanoparticles we had. We did TEM, and we found out that these particles were praseodymium 6-oxygen-11, a very nice phase, active catalyst for several reactions, and one of them is the oxygen evolution. Also, it's clear from the EDX here that the praseodymium is the one that is exhausting all the other materials they are sustaining to the cycle. And we want to understand a little bit more. So what we did, we suspected that the electrolyte was the one that was interacting with our electrode and causing somehow through this chemical interaction, this exsolution. The exsolution as a concept is usually made driven by defects that, as Professor Irvine showed us yesterday. In our case, the interaction with the cerium-containing electrolyte caused exsolution of praseodymium. So this actually shows, and it's something that is not often reported, that the selection of the ceramic electrolyte for your process could be detrimental also for the performance of your electrode, not only about the conductivity that you want to have. So we should take into important consideration, particularly with the material that we are handling in this case. Another interesting aspect is that the calcium doping and the acid treatment enhance the rate of exsolution of praseodymium. Why this happened? because with acid treatment, you are creating more edges, so you have more defects on the surface, so more nucleation sites for the transferrin. And you see here that the particles could reach up to 800 particles per square micrometer, quite interesting and never reported before as a microstructure, just by sintering the cell into an oven for the ambient temperature. Okay, all this nice, very nice story, Vasilis has told us, but the question is, what's about the performance? So we made button shells. This is the configuration that we have at the University of Groningen with the furnaces. This type of setups, they are connected with a gas chromatograph and a mass spectrometer. So we can analyze also the products that are coming out of the cell and evaluate Faradaic efficiencies. And this is the performance that we took. Use of the colors are corresponding to what I said before. We have the regular PNC here with the darker color, the light fade. You see the performance is increasing, higher currents for the same amount of voltage. The same with the doped sample, they are even better. So practically, if you see the results, we could even double the performance of the perovskite that we found in literature just by a simple amount of calcium doping and acid treatment, something very simple techniques in order to functionalize its performance. What about Faradaic efficiency? This is another key element for us. We want to make protons. The Faradaic efficiencies below 1 ampere exceeded 90%. As you are increasing the current, Faradaic efficiency decreases, but this is points for also for other discussion in a different presentation. Also, the materials were quite stable. We did the performance for several hours. You see here that we tested the best calcium doped material for more than 120 hours. It's the same sample like this one. So initially we tried with different current densities and then with continuous study. And then we also checked the interface after the test. We can still see the nanoparticles. This is the electrolyte, the ceramic electrolyte. This is the electrode. And you can still see the particles there, a little bit larger compared to what we had in the beginning, and a little bit more solution compared to what we have. So we had even more interaction with the electrolyte, but the performance was quite stable. So why we selected this type of current densities, as you see here, the Faradaic efficiency was very high. There is no point of doing characterizations of very high current densities where the Faradaic efficiency for protons is very small. And therefore we selected to go to current densities where we practically produce only protons. So to conclude, I think the first important point is that we can use this type of electrochemical membrane reactors like the concept of the olefins. They can unlock industrial electrification at intermediate temperatures. This is very important, and they are also show the uniqueness of these type of devices. In order to do that, except of efficient conversion of CO2 or nitrogen, we want to have steam electrodes that they can deliver the amount of protons that they are required for these reactions. And for that, we need very efficient materials also for steam electrolysis and intermediate temperature. We could do something like that by using ceramic materials that they possess triple conducting properties, ions, protons, oxygen, anions. In this case, we took a rather simple structure like praseodymium nickel cobalt perovskite, and with simple and rational doping and functionalization through acid, we managed to increase its performance significantly. We also observed something completely new, which is the exsolution of praseodymium just by sintering the effect and through the interaction with the electrolyte. And this is something under investigation currently in our group. And the electrocatalytic test, first of all, showed that we could achieve the targets and the KPIs that we set for olefins for the steam electrode. That's why now this will be delivered to partners for further testing and scaling. And as you can see here, we have 0.45 amperes per square centimeter at 450 degrees, which is quite interesting. And with that, I will just close by acknowledging, of course, now it moves fast. acknowledging all the partners from the Polythins project, and particularly the people that you see here that we collaborate on this specific job. Thank you for your attention, and sorry for this trouble, because I know how annoying it can be. I do that all the time. Thank you.
Thank you for the very kind presentation. There are questions? Yes?
Growing busy material is Thanks for your presentation. Your NPC material is P or N type? Okay. Because I saw you put electrons, so it shouldn't be holes.
Yeah, so one of the biggest problems that we have when you do steam electrolysis, particularly in oxidizing environment, is that you are losing the Faraday efficiency. And the Faraday efficiency means that either you conduct protons or electrons in this case. You're absolutely right. That's why also when we have continuous operation, there are tons of research out there. You will see current densities of 5, 10 ampere. That doesn't make any sense to me. What makes sense is that you put your gas chromatograph and you measure how many hydrogen or how much products you have from your reactor. In our case, we use a high Syria content electrolyte, which has, among the reported, the smaller number of electron holes and the highest Faraday efficiency. And this is what we observe. When we have zirconia-rich electrolytes, we have lower Faraday efficiency.
How you fabricate your electrodes? Screen printing?
The powders,
Classical. No, the cell.
the cell. The cell I cannot disclose exactly, but it's quite basic. It's we make the pellet, the green pellet. We take cast the electrolyte, and then we co-sinter at a very high temperature, and then we start the process with barium stuff. But that we have special ways to treat it because the barium can evaporate quite easily.
Thank you.
Other questions? No, thank you very much. Very welcome. And now the presentation from Daniel Elmery, Modelka, a cloud-based membrane unit operation for process simulation environments.
It works.
It's just.
Great, awesome.
Oh, nice.
All right, hi everyone. Everyone's still alive, awake, alert, enthusiastic? Kind of, maybe a little bit? Yes, okay, good. Well, so my name is Daniel. I am a software engineer at Modelka, so this talk is going to be a little bit different, I guess, from what you're used to. But luckily for you guys, I'm also in the final stages of my PhD at the group of postgraduates, so you know we're still academics here, I guess. All right. So this talk will be about our cloud offering, which is a cloud-based membrane block for Aspen. I could make it also a little bit educational. I'll also put in a few ways in which you can interoperate with Aspen to make it do things it cannot do. But before we dive into what Aspen is, how it works and everything, let's start with this. So membrane technology helps to meet many challenges of a more sustainable economy. I think most people here can agree on that. But also on the fact that it hasn't really quite lived up to most of the promises yet in industry. So some of the applications, you know, are fairly straightforward. It's used for CO2 capture, electrolyzers contain membranes, water purification is possible with membranes, hydrogen, well, you name it. There are so many ways to do this. But then I would also like to show this slide again that also Fausto, I think, showed in his presentation, which is that there's a fairly sizable gap between what is possible in academia, and then there's a big valley of depth of investment before you reach the stuff that actually reaches industry. So under the project Macbeth, which started, I believe, 4 or 5 years ago, something along those lines, we were founded Modelka as a spin-off of Eindhoven Technical University and Polymit in Milan. So both Eindhoven and Polymit had a fairly sizable body of membrane models that could help to prove if technology works or not. And they decided to put all of that into this company link it up with a bunch of industry partners, and then see if we could make it fly. So any industrial interest, of course, starts with a solid business case. In the end, they need to make money. A lot of facilities in the chemical industry run for 40, 50 years before they're due for major maintenance. So you need to be really sure that that's worth upending. So to make a business case, of course, you need to do a bunch of calculations. You can't just go there and say, like, look at how beautiful my membrane looks. Nobody's going to buy that. So you need to be able to show that it actually makes money. So we want to make these types of calculations accessible to industry. And we also want to empower academics to put their models on our platform so that they can also show industry that it works. So for these membrane models, the basics are actually not that difficult, right? I mean, you can fairly easily do a calculation on the back of an envelope of whether your membrane will make sense or not. But these are very hard to generalize because, you have a myriad of materials. The material scientists here will also know that a lot of materials, even in the lab, are hard to, generalize. One day the moon will be in a different place and then your membrane might not work. But there's also mixture compositions that affect the performance. There's process parameters, and all of these, of course, interact. High temperature might burn your material for good or for worse, for better or for worse. So I guess this is a good moment to tell you about Aspen. So for the people who are not process engineers in here, Aspen is pretty much, could say, the Microsoft Office of process engineering. So it's a way in which you build your processes. You get these blocks that might represent a distillation column or some separator. You connect them up, you put some material in, and it will calculate how much your energy uses, how much your material uses, et cetera, et cetera. And it's an entire suite that, basically allows you to operate a chemical factory from the design to the final operation. So the funny part about Aspen is that Aspen does not really contain a good solution to model membranes. There's what they call a separator block, but it's very basic. And the reason for that is because of what I put on the last slide. It's very hard to generalize. So for Aspen to make all these separate cases, it doesn't really make sense for them. They just want an easy solution. So if we could make something in Aspen that you could use for your membranes, we would, catch two birds with one stone, which is there's a lot of reinventing the wheel in academia being done. If you get a standardized tool, you will not have 10 master students re-implementing their kinetics to get everything working again, and then figuring out where the discretization doesn't work anymore. And then for industry, before they have to hire expensive specialists, like people who get a PhD in membrane science, they can do some estimates to see if it actually makes sense to get these people on board before they actually do. So we set out to develop an ergonomic, so easy to use, customizable, so you can tweak it to your own process, membrane unit operation that works standalone, so that you're not necessarily locked into Aspen. If you want to use something else, it's fine. You want to use it in MATLAB or Python or whatever you want to use nowadays. That works standalone and also with all the other stuff that you might want to use. So our goals for that was to make a nice graphical user interface with it, to make it customizable, so that you can select some diffusion models, maybe some geometry or kinetics that are specific to your process. But then also the expensive specialist part, we also have some specialized models that we have from our model database. If you really need something for palladium that's super good for palladium, we can also offer that. So how are we going to make Aspen do all of this stuff? So we start with that. So the easiest way to do this is something that Aspen offers out of the box, which is Excel. So you can link Aspen to Excel. You can give it some inputs. It will give you some outputs, and then you can do, for example, some energy calculations. You don't need to be a great programmer to do this. You can just use the Excel interface, which is nice. And then if you want to send it to your friend, you can easily do it too. So it's actually pretty nice, but it's very limited in what you can do, unless you do the world championships in Excel, which is an actual thing, by the way. Yeah, it's fairly slow. And also, you know, there's a bunch of PhD students and master's students who manage to couple this also to MATLAB, by Visual Basic and Python and all these things. But it's, you know, this is a bit hacky, and if you're industrial partner, you want something to work, this may be not the best way to do it. Yeah, so, you know, this is an example. People can make beautiful things in Excel. So another one is Fortran. Fortran is a fairly old programming language, which there's a ton of stuff built in it, but it's a bit outdated. We'll skip over this fairly quickly. This is one of the best ways to do it, I guess, but it will still lock you into using Aspen, so that's not really an option. So then there's this. So COM. This is probably the most technical slide of all of them, so bear with me for a second here. So COM is a Microsoft standard that lets programs talk to each other in a way. So it's a bit of a universal language that allows different software applications to communicate. So Aspen Plus, for example, has a COM interface, and then you can use Python or Visual Basic or MATLAB. If you're a chemist and you use ChemDraw, ChemDraw also has a COM interface. You can automate the hell out of ChemDraw if you want. I'm not sure why you would, but you can. And then, of course, you can use Python to do this, but it will pretty much only allow you to control Aspen. So you can start it up from COM, you can, you know, load your sheet, and then run a bunch of calculations. One of the nice things is you can do an optimization, for example, you know, 10 flow sheets at a time instead of doing it manually one by one. But still, you don't get this nice graphical user interface, you don't get the block, and all that kind of stuff. And third, Cape Open. So this little Wikipedia thing here. So it's actually quite old. This is a standard that partners from industry and academia came up with because they recognize this problem. You know, that it's not easy to build something if you're Plaza and you want to build your reactor really truly in Aspen. It wasn't possible before they came up with this. So this is actually based on COM that I just said. So you can link up with this and you can use this to build some of your tools. But the reality of this is that you need to be a pretty good programmer to do this already. So if you're a tech-savvy PhD student, you could probably do this, but it's not for the masses. Yeah, especially, you know, if you don't have the time to do all this, so you just want something to work. Luckily, we did all of this nasty work for you. So this is actually what we use to build our block. We interface with this Cape Open software that also makes it compatible with other simulators besides Aspen, like ProSim or IWSCT, or what have you, all kinds of things. So then we have our graphical user interface that we can build. And we'll talk to Cape Open for us. You can customize it because we control all the programming in the background. And that's how we also deliver tailor-made process models. So we have this Modelta Cloud block. So it's actually just a block in Aspen that you can drag there. When you open it up, this is a very early version, by the way. But just to give you an idea, you can select models from our model database. One of them is the Palladium model. We also have versioning because we know that academics really love their reproducibility. So if we change something along the lines, it's not like your calculation next year is going to be different from today, even if we improve things. So you can run it anywhere. Actually, you can even run it in your web browser if you wanted to, or on your phone, or maybe on a PLC or your fridge if you like to. So you can really run it anywhere. It has a graphical user interface that you can use. You don't have to do any programming anymore. And it's all in a single block. So from our one block, you can select your Palladium model. You can configure something yourself. Yeah, well, at least that's where we're going right now. So you don't get the whole toolbox in Aspen where you need to do all these things again. So now you're probably asking yourself, why are you doing this in the cloud? So there is some good reason for this. We actually thought about it because we know it might also turn people off to using our software. But the reality of it is that a lot of models nowadays are getting more and more computationally expensive. If you go more dimensions, it becomes more computationally expensive. If you want to do machine learning applications, which are all the rage nowadays, you may not have a super good accelerator in your work laptop that will actually allow you to do that. But in our cloud, we can easily give you all the hardware you need. And that also makes it platform agnostic. So that's why you can run it on your phone or your fridge if you wanted to. It also allows us to keep the cost down a little bit because it's a bit of a pay-as-you-go thing. If you use it a lot more, you can pay more. If you use it less, you can pay less. So if you only need it for like a 3-month project, you get a license for 3 months, and then after that, you can just cancel. We can instantly update our stuff. But more interestingly, what we also plan to do is to offer our block, like I said earlier, as a platform for people to offer their models to other people. So you no longer have to upload your MATLAB script somewhere to GitHub for some people to find it. You can just put it on our platform and we can run it for you. It will instantly be delivered to whoever is our customer. Okay, so I'm not sure. I have a little bit of a video here to show you that this actually does work. So when you open our block, you get this little model selector. Now it has a default model. It will configure the block with the proper inlets and outlets. So this will also change when you change the blocks. You click the play button in Eindhoven, you'll get a nice little pop-up that says calculating. Or it's Aspen because it also takes a while. And then the results eventually will be returned from our cloud to our block. So this is also made in such a way that you could also do this in Python. So you could just send your process model in Python to our cloud. It will return some answer and you can do with it whatever you like. Yeah, so we are targeting a release for early next year. So we're still developing this very actively. So we're looking to put, of course, all of our models in the cloud eventually. We're building out these customizable models where you can, get board diffusion or, solution diffusion or workflow, what have you. The reaction kinetics, of course, very important. Models of partners. So if you have models lying around, please do let us know. Yeah, and a standalone application. So like I said, if you'd like some updates on what we're doing, how this is progressing, or if you have something that might be worth monetizing in the future, please connect with us on LinkedIn. Let us know. We'd be very interested to talk to anybody who would be interested. Also, if you have any input, of course. Thank you.
Thank you for your presentation. Questions? Comments? Positive? No? Yes? There is one.
Thank you for your presentation. So I just thought to ask, if I understand you're a software engineer. So yeah, what is your main role in all this when you're also a PhD student with us? Yeah, because I know for this it's a lot of equations and modeling and all that. So for you, how is it like and what do you really do?
So my background, even before I started working on my PhD, I've been developing scientific software mostly for analysis of simulations. And in my PhD, I went more into the machine learning direction. So I am not a process engineer. So in this case, I mostly developed this package. So I do the cloud port and the actual integration with Aspen. So it requires some understanding of how processes work, but not super in-depth, of course. And it requires a lot of software engineering knowledge, which I do have. So that's what my role is. I'm very much on the software engineering part. And my colleagues are the people who actually develop more of the models. So they're more in the physics and the process engineering part. But some multiple expertises here and there. Yeah. But of course, we're a fairly young company and a small team, so everybody has to wear multiple hats. That's what goes up in the startup life. Yeah. Does that answer your question?
There are no other questions. Thanks again to our speaker and thanks to all the speakers of the afternoon. And now I don't know what will happen.
Now we will wait for the people from the other room to join us,
And to
and we're
close.
going to have a closure.
Okay, thank you.
So please stay in the room, or if you would like to go to the toilet, then fine. But we have something more, not until the finish. Okay.